Hi, today I'll be doing a presentation on the topic Avl Trees as a part of my digital assignment under the course Data Structures and Algorithms. Binary search tree is a node-based binary tree data structure which has the following properties. The left subtree of a node contains only nodes with keys lesser than the node's key. The right subtree of a node contains only nodes with keys greater than the node's key. The left and right subtree each must also be a binary search tree. Every BST operation is of the order d, where d is the depth of the tree. For a binary tree with n nodes, the minimal d equals t is equal to log n to the base 2. A BST operation's best case running time is therefore order of log n. The worst case running time of a binary search tree is order of n. What takes place when items are inserted in an ascending order into a BST? So what happens is a lack of balance occurs. The following are the examples of balanced and unbalanced binary search trees, where the most right one is a balanced binary search tree, the one in the middle is an unbalanced right skewed binary tree, and the one on the left is a balanced binary search tree. Balancing binary search trees. Many algorithms exist for keeping binary search trees balanced. Some of them are Avl trees, which are also known as height balanced trees, splay trees and other self-adjusting trees, B trees and other multi-way search trees. In this presentation, we'll be focusing on Avl trees. AVL trees are good but not perfectly balanced. AVL trees are height balanced binary search trees. The balance factor of a node is the height of the left subtree minus the height of the right subtree. An AVL tree has a balance factor calculated at every node. For every node, heights of left and right subtree can differ by no more than 1. Height of an AVL tree. N of h is equal to the minimum number of nodes in an AVL tree of height h. If height of an AVL tree is h, then the maximum number of nodes can be 2 raised to power h plus 1 minus 1. Following are a few formulas concerning the height of an AVL tree. Here we have two AVL trees, both of height 2, and the balancing factor for each node is calculated and shown in front of you using the formula height of the left subtree minus height of the right subtree. After inserting 7 to both of the trees, we observe that tree A still remains balanced, whereas tree B is not balanced now, as at the node 9 the balance factor is 2. Insertion and rotation in AVL trees. The insert operation may cause the balance factor to become 2 or minus 2 for some node. Only nodes on the path from the insertion point to root node have possibly changed in height. So after the insert, go back up to the root node by node, updating heights. If a new balance factor, that is the difference of the height of the left subtree minus height of the right subtree, is 2 or minus 2, adjust the tree by rotation around that particular node. Following is an example of single rotation in an AVL tree. Here, the tree rotates about the node 9. Rotations in AVL trees. There are 4 cases in rotations, out of which 2 require single rotation and 2 require double rotation. Under single rotation, insertion into the left subtree of the left child of alpha causes LL imbalance, which can be fixed by right rotation. Insertion into the right subtree of the right child of alpha causes RR imbalance, which can be fixed by left rotation. Under double rotation, insertion into the right subtree of the left child of alpha causes RL imbalance. insertion into the left subtree of the right child of alpha causes LR imbalance. The rebalancing is performed through four simple rotation algorithms. Let's talk about the outside case insertion in an AVL tree. Consider the AVL tree given in front of you. In this AVL tree, if we insert anything into the node X or Y, it destroys the AVL property of the tree at node J. Now, on inserting an element into X, we find that LL imbalance occurs. To fix it, we need to perform a right rotation at node J and restore balance. Here's an animation showing right rotation to restore balance. Now that the right rotation is done, the LL imbalance has been resolved and AVL property has been restored to the binary tree. Now we'll talk about the inside case insertion in an AVL tree. Consider the valid AVL subtree given in front of you. Inserting an element at the node Y destroys the AVL property of the tree at the node J. Do you think right rotation will restore balance? Let's try it out. As we can see, the right rotation did not restore balance in this case. It caused K to go out of balance. Consider the structure of subtree Y. Now we will do a left-right double rotation at node J. After the left rotation, now we will perform a right rotation at node J. After the double rotation has been completed, we can observe that balance has been restored to the AVL tree. There is no need to keep the height, just the difference in height, that is, the balance factor. This has to be modified on the path of insertion even if you don't perform rotations. Once you have performed a rotation, single or double, you won't need to go back up the tree. When we insert at the leaf, only nodes on the path from insertion point to root node have possibly changed in height. So after the insert, go back up to the root node by node, updating heights. If a new balance factor, that is the difference in the height of the left subtree minus the height of the right subtree, is 2 or minus 2, adjust the tree by rotation around the node. Here are a few snapshots for codes for insertion in binary search tree and AVL tree. Now we'll take up some examples of insertions in an AVL tree. Consider the tree in front of you. It follows the AVL property. Now we'll insert 5 into this tree and see if it would still follow the AVL property. We observe that after inserting 5, it still follows the property of AVL. Now we will insert 40 into it and see what happens. After inserting 40 into the tree, it's still following the property of AVL. Now we'll insert 45. After inserting 45 into the tree, we observe that an imbalance has been created at the node 35, which arises the need for a single rotation. After single rotation, we observe that the Avl tree has been balanced. Now we'll insert 34 to this balanced Avl tree. After inserting 34 into the tree, we observe that an imbalance has been created at the node 30, which arises the need for a double rotation. After double rotation, we observe that the tree is now balanced. Deletion in an AVL tree. Deletion is similar but more complex than insertion in an AVL tree. Rotations and double rotations are needed to rebalance the tree. Imbalance may propagate upward, so many rotations may be needed to restore the balance. Now in the end, we would like to discuss the pros and cons of AVL trees. Arguments for AVL trees. Searching in an AVL tree is order of log n since AVL trees are always balanced. Insertion and deletion is also order of log n. The height balancing adds no more than a constant factor to the speed of insertion. Arguments against AVL trees. Difficulty to program and debug, more space for balance factor. Asymptomatically faster, but rebalancing costs time. Most large searches are done in database systems on disk and use other structures, for example, B trees. It may be okay to have ON for a single operation if total runtime for many consecutive operations is fast. Example, splay trees. Thank you for watching the presentation. Special mention to our professor, Dr. Kalyana P., for giving us this opportunity, which allowed us to go into the depth of AVL trees using animations in PowerPoint.